Declared the header files which will be required for the various functions that we are going to use. The very first thing you can see is the semaphore declaration of this array chopstick. Since there were 5 chopsticks, so I have declared a semaphore variable for each one of the chopsticks. Then there are 2 functions which we are going to define later. One is philos for the philosophers, and second one is the eat function. So we will see the definition later on. In the main function, the very first thing that we are going to do is we are going to declare this pthread variable. Since there are 5 philosophers, so I'm going to represent every philosopher with one thread. So I'm going to create 5 threads. So that's why this array of 5. Now there are 3 for loops that we have used. The first for loop is to initialize every semaphore variable that we have declared. So if you can recall, we need to initialize the semaphore variable. So 3 parameters it takes. The variable 0 means we are not sharing it among processes, and 1 is the initial value of the semaphore variable. So each of the chopstick is initially free. 1 means that each chopstick is initially free. The second for loop is used to create the 5 threads. So I have just put up the pthread underscore create function in a loop so that all the 5 threads are created. Now while creating the thread, so you can see that I have passed here ti. Okay, so this means that the loop will go from 0 to 4, 0, 1, 2, 3, 4. So the philosophers will be t0. So the value t0 means the 0th philosopher, t1 means the first philosopher, and so on. And the fourth parameter here, which is the input to this philos function, is ni. I means if I am going to create the 0th philosopher, the value that is going to be passed to this philos function is 0. For the first philosopher it will be 1, for the second philosopher it will be 2. So you will see later why this is important. And in the last for loop we are going to use the pthread underscore join function for each of the 5 threads. Now coming on to the first function, which is philos, there are a lot of printfs that I have used. Otherwise the key statements are only limited ones. One is this semWait, again semWait, call to eat function, semPost, and semPost. Okay, these are only the 5 key statements here. Even the sleep function, so 6 key statements are there. Printf is just to show you that how the steps are being executed, or how each philosopher tries to pick up the sticks and then put them down after eating. So what will happen is, let us suppose that it is the first philosopher that wants to eat. So just recall the diagram. This is it. If it is the first philosopher, he needs to pick up the chopstick number 1 and chopstick number 2. Pickup means that he is going to initiate the wait function on the chopstick 1 and then wait function on the chopstick 2. So let's see what happens. Now whatever is the value of n that we have passed to this function will be stored in ph. So which is the value passed? It's the value I. Okay, so for philosopher 1 here th will be 1. So what I will print, philosopher 1 wants to eat. Okay, so whenever any philosopher wants to eat, you will see a message on the screen that this particular number philosopher wants to eat. Now for eating, he needs to pick up first the left chopstick and then the right chopstick. So let us assume that here ph is 1. So philosopher 1 tries to pick up the left chopstick. What is the left chopstick? It's the number 1 chopstick. So next we use the sem underscore wait function on the chopstick number 1, that is on the left chopstick. So the philosopher will try to pick up the left chopstick. If sem underscore wait is successful, then it will move to the next statement. So philosopher 1 picks the left chopstick. So if he is able to execute the wait on the left chopstick, that is chopstick number 1, this message will be printed, and then the philosopher will try to pick up the right chopstick. Similarly, we are going to issue sem underscore wait on the right chopstick. Now right chopstick is the chopstick number 2. So that's why I've used here chopstick pH plus 1 mod 5. pH is 1. I'm assuming that I'm doing this for the philosopher number 1. So 1 plus 1, 2. 2 mod 5 is 2. So if this weight is also successful, this means that the philosopher picks the right chopstick also. So if the philosopher is able to pick the left as well as the right chopstick, this means he has both the chopsticks now and he can eat. So we call the eat function. So from this point onwards, from this eat, the control will go to the eat function. And let's see what is there in the eat function. So eat function contains nothing, just a printf, that philosopher, whatever number. So like for in this example, I'm assuming it is philosopher number 1. So philosopher 1 begins to eat. So this will print on the screen. Once this function is over, the control will come back. Then I have used sleep for 2. Why I have used sleep 2? Because by using this sleep function, this particular thread will go to sleep, and this will give the chance to other threads to execute at the same time. Okay. So what I mean here is that if, let us suppose philosopher 1, so if the thread number 1 gets into the eating state, then I will give 2 seconds to this thread to be in the eating state. Now within these 2 seconds, some other thread will also try to eat, and then we will see whether the adjacent ones are able to eat or not, which they should not be able to do. So what I mean is, if philosopher number 1 is eating, then philosopher number 0 and 2 should not be able to get into the eating state. Now once the eating is over, then what? We need to put down both the chopsticks. So first I'll print philosopher has finished eating, then you issue sem_post on the chopstick number 2 or pH plus 1 mod 5, whatever is the number of pH or the philosopher, and then you put up the second chopstick also. Okay. So once again, initialize the semaphore variable on each of the chopstick, create 5 threads, and then join those threads. Okay. While creating the thread, make sure you pass the same number, that is the number of the thread. Okay. Then within this philos function, what we are trying to do is, we are first trying to pick up the left chopstick. So whatever is the number passed to this function, the chopstick to the left of that philosopher will be picked first, then the chopstick on the right. If both these chopsticks are available, then the philosopher will eat, sleep for 2 seconds, means be in the eating state for 2 seconds, and then put down the right chopstick first and then the left chopstick. Okay, so let's see how this runs. So compile the program, dpp.c -lp thread, because we are using the threads, and then run this /a.out. Now let us understand this output. Now in this case, the philosopher 0 is the first one who wants to eat. So philosopher 0 tries to pick left chopstick, and philosopher 0 picks the left chopstick. Then philosopher 0 tries to pick the right chopstick, and philosopher 0 picks the right chopstick. So if he is able to pick both the left and the right chopstick, so then philosopher 0 begins to eat. Now remember this, if philosopher 0 is eating, so this means chopstick 0 and chopstick 1 are occupied. So if now while he is eating, this is sleep of 2 seconds, so one of these 1, 2, 3, 4 can try to eat. If 1 and 4 tries to eat, they should not be able to do it, because they will not be able to pick one of the chopsticks. Alright, philosopher 1 will not be able to pick chopstick number 1, philosopher 4 will not be able to pick chopstick number 0. But 2 and 3, if they try to eat in this time, they can do it, right? So let's see. Now after that, philosopher 1 wants to eat. So philosopher 1 tries to pick up the left chopstick. Philosopher 1 tries to pick up the left chopstick. Can he do it? No, because chopstick number 1 is already being used by philosopher 0. So that's why there is no output as philosopher 1 picks the left chopstick, because philosopher 1 is not able to successfully execute sem_wait on the chopstick number 1. Philosopher 2 now wants to eat. So philosopher 2 tries to pick the left chopstick. He is able to pick the left chopstick. Then he tries to pick the right chopstick, picks the right chopstick, and philosopher 2 begins to eat. Alright, so we have implemented what was expected in the dining philosopher's problem, that the adjacent philosophers should not be able to eat, but others can do so. So what we have done is, while philosopher 0 was eating, 1 is not able to eat and 2 can eat because the chopstick number 2 and chopstick number 3 are both available. Now until and unless either 0 or philosopher 2 puts down the chopsticks, no one else can eat. So you can see here 4 wants to eat, tries to pick up the left chopstick, that one is free. 4 picks the left chopstick, tries to pick the right chopstick. So chopstick right is 0, that's not free. That's why he's not able to pick the right chopstick. Okay, there's no output here. Similarly 3 also fails to pick up both the chopsticks, and then 0 has finished eating. Okay, once 0 has finished eating, so 0 leaves the right chopstick, 0 leaves the left chopstick. Okay, and now if 0 has left these, this means chopstick number 0 and 1 are free. Okay, and now I think it will be pretty easy for you to understand the rest of the output. Okay, so you can just go like this. Alright, one more thing, if I rerun this, and you can see that the output is different now. Okay, so same thing you will observe in your system also. The output will not be same, but you can understand the output just in the manner I have explained you above. Whichever philosopher is able to pick both the chopstick, he will start eating, and the adjacent ones will not be able to do it. That's what is happening in this case also. So I hope that this program or this implementation of the dining philosopher's problem is clear now, and you will be able to write the program and implement in your lab or in your exam. For more details regarding this dining philosopher's problem implementation, you can visit this link where you can find the program code and certain Viva questions also. As usual, keep watching, keep sharing. See you in the next class.